Well, good afternoon, everyone. My name is AndreaRodriquezFlores. Please pardon my voice. I'm getting over a cold. For my final project, I trained and deployed a deep learning model that could identify damaged buildings after the Palisades fires earlier this year. So what exactly happened during those fires? Well, the fire started on January 7th and burned for 24 days before it was contained, destroying most of the areas of the Pacific Palisades, Topanga, and Malibu. It burned nearly 24,000 acres, killed 12 people, most of whom were first responders, and destroyed nearly 7,000 structures, becoming the most destructive wildfire in the history of the city of Los Angeles. Among those 7,000 structures were mostly single-family homes, multifamily units, apartment buildings, mobile homes, businesses, and public infrastructure. Entire neighborhoods and their infrastructure were gone in less than a month. But how do we know that? How do we keep track of a toll that's obviously so large? Currently, FEMA, California Wildfires through Firescope, and the Damage Inspection Database of California have standardized criteria that personnel have to follow. But overall, firefighters and emergency responders have to visit each property individually and collect data manually on each structure's condition. However, for a fire that burned for 24 days, the terrain, vegetation coverage, and just the sheer extent of the fires made locating and identifying structures nearly impossible. And honestly, it's no wonder. This is Maxar satellite imagery of an area above the Pacific Palisades before the fire. This is that same neighborhood after the fires. You could even see that there's still an orange haze hanging in the air after everything had burned. Preliminary damage assessments save lives. For the emergency responders on the ground, having access to as much information as possible about a post-disaster setting could be the difference between life and death. For families, it could be the difference between knowing if the area their homes are in is safe, or for a lot of people, if they even have a home to return to. Yet it relies heavily on trained ground crews conducting visual inspections. I mean, we're talking about a process that can be inefficient, dangerous, and labor intensive in areas with severe destruction, hazardous conditions, or debris. I mean, just imagine what it was like during those 24 days of what firefighters called hell on earth. But when there's a will, there's a way, isn't there? That's where GeoAI comes in. We know things are getting worse. Climate change is bringing more wildfires, more hurricanes, more tornadoes, and more disasters. But advances in remote sensing platforms have enabled us to use computer vision and deep learning techniques with incredible accuracy levels. At the heart of this is the convolutional neural network. Convolutional neural networks are designed to process data in the form of multiple arrays, exploiting the natural property of signals to arrange themselves into what are called compositional hierarchies. Now, what the hell does that mean? Well, in a compositional hierarchy, higher level features are built out of simpler, lower level ones, and we can extract those lower level features to train a computer to detect patterns. Let's think about what makes a house a house. Houses have roofs, they have windows, they have a driveway, some of them have trees. Most of those, the more of those smaller level features that an input image has, the higher the probability is that it's a house. This makes convolutional neural networks a natural choice for feature identification and classification. They're made to detect patterns that form naturally in remotely sensed imagery. In fact, they have so much potential that deep learning models using convolutional neural networks are already available in geospatial applications like Esri's. In this project, I wanted to put those GeoAI tools to the test. I wanted to test how effectively Esri's deep learning tools could be applied to the damage assessment process and showcase what the results that I got reveal about the capabilities and limitations of this technology when applied to the assessment process. So at the start of the semester, I figured that since, this fire was so fresh, it would be a good place to start. I picked the two most important neighborhoods in Los Angeles and a little tiny bit beyond, the Pacific Palisades and the Sunset Mesa neighborhood areas. The feature classifier that I trained in this project requires only two inputs, a high-resolution raster and a feature class layer that defines the boundaries of each feature. Using these files, I based my process for training and deploying the model on Esri's deep learning workflow for object classification. First, I prepared the imagery, I made a training data set, I trained the model, I used the model, and I prepared my model's results for accuracy assessment. It sounds simple enough, right? Well, the deep learning tools require a GPU with about 16 gigabytes of dedicated graphics memory. The minimum is 6, but they really recommend that you go with 16. My computer has 4 gigabytes of dedicated graphics memory, so I had to get really creative. This is where I came up with what I call the cookie cutter method, or the CCM. First, you consider your computer's capabilities. Mine only has 4 gigabytes of dedicated graphics memory, so I have to cut my data into subdivisions. As opposed to analyzing a large extent, which is any geospatial scientist here know is really resource intensive, the cookie cutter method subdivides the study area into digestible little cookies that the computer can handle, decreasing the analysis runtime and ensuring that there's no errors in the tool. Finally, you merge all of your layers once your inferencing is complete. So I started with a high resolution raster. My raster imagery is a 31 centimeter resolution Maxar satellite mosaic of the northmost portion of LA. As you can see, I trimmed it down quite a bit to cover the boundaries of my study area because analyzing a huge image like that, impossible. And I got my building footprint data from OpenStreetMap. And I found that I had to use an archivable file because the most recent ones, even in January when I started my project, were already updated with missing buildings by the community. And I attached the zoomed in version so you can see exactly what those little tiny building footprints look like. And then this is what all of those layers look like once you've cut them with the cookie cutter method. I subdivided my data into 20 parts based on a polygon layer that I cut to sort of my cookie cutter. And I ended up with 40 layers that I could then input into my model after I trained it. And then to train the model, I created a schema with 2 classes, damaged and undamaged. Then I went through my untrimmed imagery and I picked a total of 2,000 buildings for each class. So 2,000 damaged, 2,000 undamaged. I picked buildings of various shapes and sizes since the final model would consider these factors when generating a classification. Houses all tend to look pretty different, so I wanted to have a diverse data set. And then once I had my image chips, which is what all these little tiny houses I picked up are called, you then train your model with the tool. And the training showed that the Palisades model improved steadily and consistently over the 26 epochs that it took to train. When it stopped improving, it stopped training to avoid overfitting, and it performed with a 99% accuracy on its last epoch. And we can see here this learning curve. We want these two to match and like get together. If it goes over, it means that it's undertrained, and if they cross, it means that it's overtrained. I saw that a little bit of a skew showed up, showing that it had a really tiny chance of misclassifying a building as damaged when it was actually undamaged, which is something that I see pop up again once I actually ran my data through the model. And then once I ran all 40 layers through the Palisades model, uh, I then put them into a neat little map, just like this one, after merging all 20 of those input layers. But this looks all cute and pretty, right? But how do you know if these results, because all you get are these little boxes that are red or green, damaged or undamaged. But how do you know if these results that you got are any good? Well, the most common way of assessing a model's accuracy is through the confusion matrix, which is an apt name. I used an equalized stratified sampling method with 500 samples in each class with my ground truth manually. The confusion matrix showed that the model has a tendency to underreport buildings as undamaged while over-predicting buildings as damaged. I saw this during the training, so I wasn't really too surprised. The main metrics shown in a confusion matrix are user's accuracy, producer's accuracy, your overall accuracy, and then your kappa coefficient down here. User's accuracy tells us how likely it is that what we see has been classified on the map by the model is accurate. These are known as errors of commission, where the model identified buildings incorrectly when only looking at a certain class. So when considering only damaged buildings, it identified buildings as damaged correctly 98% of the time and incorrectly marked the other 2% as undamaged. However, it struggled when classifying buildings as undamaged, only hitting the mark 90% of the time for undamaged buildings and marking the remaining 10% as damaged. This is that overrepresentation of the damage class that I mentioned previously. And then for my producer's accuracy, on the other hand, it shows our errors of omission. It represents the probability that a feature on the ground is correctly classified on a map. So it includes both the damaged and undamaged classes. For the damaged class, only 90% of buildings it included were actually damaged. The rest were undamaged buildings which were wrongly classified. Conversely, 98% of the buildings it included in the undamaged class were undamaged, with the other two having been omitted from the damaged class. Overall, the model performed with a 94% accuracy and had a high kappa score. And your kappa score just indicates that the model's predictions had a near perfect agreement with ground truth data once chance was factored out, meaning it didn't just randomly assign classes and happened to get a high score. It actually did what it was supposed to do. And I've given you a lot of numbers, which so far look really good, but what do these results tell us about the potential role about Geo AI in the damage assessment process? Well, it tells us that it works. The Palisades model is able to classify buildings as damaged or undamaged 94% of the time. It's possible to integrate DLM technology into the damage assessment process with a limited budget and limited processing power, which is very promising when we're looking at the bigger picture and adding this technology to processes that already exist. I'm just a graduate student with a gaming computer using open source data, and I was able to get really good results. Additionally, the output data is highly applicable and be an excellent starting point for damage assessment crews, especially if added to standard protocol. Damage assessment data can be combined with other metrics to help paint a broader picture of the disaster zone. I'm talking about dashboards, story maps, and other services that integrate demographic data, economic data, and all sorts of other data types that would make the raw building class data that you get from something like the Palisades model even more useful to agencies. But if it works so well, why aren't agencies all over the US jumping to incorporate this magical technology into the damage assessment process? Well, there's always a catch. It's hard to know what approach might be best. There are no standardized good practices for reporting model accuracy metrics, which will make it difficult for agencies to find a suitable model or report the findings of their own model. Pre-trained DLMs aren't always the best option, meaning that emergency management agencies would have to modify pre-trained DLMs or make their own from scratch, which would then require making a really large and diverse data set, bigger even than mine. Training a DLM from scratch might be unrealistic for most agencies. Training, fine-tuning, or deploying a DLM, even with the cookie cutter method, requires a high-powered computer. CUDA-enabled data center products cost thousands of dollars, and even the most accessible GPUs are hard to get a hold of and pretty expensive. But we already know that when there's a will, there's a way. So it's not all bad. Sure, it's hard to adapt to new technologies, but regulation is built on experience. FEMA is already looking to integrate DLMs into the damage assessment process. They're on a mission to get a clear picture of a disaster zone using GeoAI within 72 hours. We're talking about a process that takes weeks, shortened down to just 72 hours. And pre-trained DLMs aren't always the best fit, but DLMs are malleable. They can be tweaked to identify damaged buildings after earthquakes, hurricanes, wildfires, and even after damage resulting from conflicts or in active war zones. Sure, training a DLM might be unrealistic for most agencies, but GIS has always needed a hands-on, collaborative approach to new technologies. Applying DLMs to new and diverse datasets could identify gaps in performance that can be fine-tuned to create high accuracy results. GeoAI is here to stay, even though its reliability in long-term studies is yet to be seen. This emerging technology is incredibly useful and becoming more accessible every day, and it won't just save time. It'll save lives. We've got more access to high resolution data and computer processing power than ever before. The Palisades model serves as a great example of where we could start using GeoAI to find solutions to some of the biggest challenges in our field. Well, thank you so much for your time. I will now be answering any questions that you all might have about my project.